imagine for a second that you spent, the last 6 months or maybe even a year developing this brilliant market-beating investment signal.
Right, like a massive undertaking.
Exactly. You've crunched these massive data sets. You've built a custom expected return forecast that actually works out a sample, and you basically got the golden ticket in your hands.
Yeah.
But then when you take that hard-earned data and you plug it into like the most popular state-of-the-art portfolio construction algorithms out there, the machine doesn't optimize it. It just, it throws your signal straight in the trash.
I mean, it sounds completely absurd, but in the world of quantitative finance, that is exactly what has been happening for years.
It's crazy.
It's an incredibly frustrating reality for active investors. You do all this work, to predict where the market is going, and the industry standard algorithms basically just plug their ears and hum loudly.
Well, today we're going to fix that. Welcome to our deep dive into a really fascinating April 2026 paper by Bern J. Webben. It's titled Beyond DePrado and Cotton, Hierarchical and Iterative Methods for General Mean Variance Portfolios.
It's a great paper.
It really is. And our mission today is to explore how this paper completely upgrades modern portfolio design. We're going to examine why the current standard methods are what Webben calls signal blind.
Right, which is a huge problem.
Huge. And then we are going to explore 3 brand new methods outlined in the paper, HRP, and CRISP. These are essentially frameworks that finally allow you to combine robust mathematical risk management with your own active investment signals.
It really is a fundamental shift for the industry. I mean, we are moving from a world where risk management and alpha generation were treated as, mutually exclusive by the top algorithms,
Right.
to a framework where they are integrated seamlessly.
I actually like to frame this deep dive as like a thrilling heist story for math nerds.
It's a heist story. I love that.
Yeah, we are basically breaking into a highly secure, mathematically locked system just to sneak our own data inside. But to understand how we're going to pull off this heist, we first need to understand why the vault is locked in the first place.
Exactly.
Okay, let's unpack this. So let's talk about the signal blend problem. Where does this start?
So to set the stage, we have to look at the 2 standard baselines that quantitative analysts have relied on for, a while now. First, there's Lopez de Prado's 2016 hierarchical risk parity, which is widely known as HRP.
Right, very famous paper.
Super famous.
Mm-hmm.
And second, there's Cotton's 2024 sure complement generalization of that method. Both of these are incredibly popular, regularized portfolio construction methods, but they have a fatal flaw if you are an active investor.
Which is what, exactly?
They only solve the minimum variance problem. Mathematically, they are designed purely to minimize risk. And to do that, they assume that every single asset in your universe has the exact same expected return.
Wait, really? The exact same?
Yeah. In the notation of the paper, they literally hard code the expected return, or mu2 equal 1. They have absolutely no mechanism built into their equations to accept an expected return forecast from you.
That is wild. It's like buying a multi-million-dollar state-of-the-art self-driving car. But the manufacturer permanently locked the steering wheel facing straight ahead.
That's entirely accurate.
I mean, sure, the car is incredibly stable and you definitely won't crash into the ditch, but it's completely useless if you actually want to pick a destination.
That is the perfect way to look at it. And in modern quantitative pipelines, whether you are dealing with factor investing or tactical asset allocation or blending different investor views, ignoring the alpha signal isn't just some neutral default setting.
Right, it's destructive.
It is the active discarding of your most valuable information. Setting MOUT to 1 throws away your primary input before the optimization even begins.
And researchers have tried to fix this.
Right.
Because the paper mentions that Cotton tried to improve on the original HRP model back in 2024.
Right. He did, yeah. Cotton introduced a continuous parameter, which he called gamma, that basically slides from 0 to 1. The idea was to create a mathematical bridge connecting HRP's binary tree-based structure all the way over to a true, exact minimum variance portfolio.
Okay, that makes sense.
It was an elegant idea, for sure. But Webben's paper points out a massive vulnerability when you apply Cotton's method to real-world data, especially on small sample sizes. Think of a scenario where your time horizon T is just 60 periods.
Wait, why does a small sample size suddenly break the math? Like, what is happening under the hood there?
Well, it comes down to how Cotton's algorithm traverses its hierarchical tree. At every internal node of that tree, Cottony's method relies on something called the Schur complement,
Okay.
and that essentially requires performing a block inversion of the covariance matrix.
Okay, stop right there. Block inversion of a covariance matrix.
Yeah.
Translate that into plain English for us. What is the algorithm actually trying to do?
Right, sorry. Think of the covariance matrix as a giant complex web showing how every stock moves in relation to every other stock.
Got it.
A block inversion is a mathematical trick to slice that giant web into smaller, manageable chunks, invert those chunks to find the optimal weights, and then substitute them back in.
Okay, that sounds reasonable. So what's the issue?
Here's the problem. When you have a small sample size, your data is mostly random estimation noise.
Oh, because 60 days of stock data doesn't give you a true picture of how two massive companies correlate over a decade.
Exactly. So your inputs are inherently noisy. When the algorithm tries to invert those noisy matrix chunks at every single branch of the tree, it acts like a magnifying glass for errors.
Oh, wow.
Yeah, it accumulates what we call condition number damage. Think of it like making a photocopy of a document. If you make a photocopy of the original, it looks okay.
Yeah.
But if you make a photocopy of a photocopy of a photocopy, which is essentially what the algorithm is doing at each branch, every tiny speck of dust, every piece of noise gets amplified until the final image is completely unreadable.
And what's the real-world consequence for your money if you use this method?
The paper documents that at intermediate gamma levels, because of this compounding damage, Cotton's method can generate out-of-sample volatility that is 10 to 30 times worse than a simple, direct Markowitz solve.
10 to 30 times worse.
Yes. The instability just spirals out of control.
So the steering wheel on our self-driving car is locked straight. And if you try to adjust the suspension, the wheels literally fall off.
Got it. Pretty much.
So how do we fix this? How do we force these tree-based methods to actually see our custom signals without breaking their computing efficiency? Because that's the whole appeal of these tree methods, right?
Exactly, the speed.
Right. They run in what computer scientists call O of n squared time, which is incredibly fast for huge data sets.
That speed is exactly why people want to save the tree structure. And that brings us to the first of the three new methods Webin introduces, which is HRP.
Okay, HRP.
This method keeps the hierarchical dendrogram, the branching tree structure of classical HRP. It keeps the computing efficiency, but it changes the scoring device at the branches.
Wow.
Instead of a standard flat inverse variance portfolio, it introduces a signed inverse variance portfolio.
Wait, why do we need a special signed portfolio? If we have our long and short signals, say, +5 for Apple and -5 for Tesla, why couldn't we just feed those numbers directly into the normal HRP tree?
Because of a devastating phenomenon Webin calls aggregate signal collapse. If you just use normal mixed sign signals inside the standard tree, the positive and negative signals literally cancel each other out when the algorithm aggregates them at a parent branch.
So if a branch contains that +5 and -5, the math adds them up and just sees a 0.
Precisely. The aggregate signal for that branch collapses to 0. And when a branch has a signal of 0, the algorithm thinks there's no return to be made there.
So it just ignores it.
Basically. It drives the budget allocation for those assets down to pure numerical noise. HRP fixes this by taking the absolute values of the signals at the branch scoring level.
So it treats a -5 as a +5 while it's navigating the tree.
Right. The tree calculates the budgets based purely on the magnitude of the signal, which completely prevents the collapse. Then it simply multiplies the positive or negative sign back in at the very end, at the leaf level.
Right, when it's assigning the final weights to the actual assets.
Exactly.
Wait, hold on. The whole point of quant finance is hedging. I mean, if we strip the positive and negative signs out of the math while it's traversing the tree, aren't we completely blinding the algorithm to our hedges?
It sounds like it, right?
Yeah, if it just sees absolute values, how does it know that a long and a short position in highly correlated assets are supposed to cancel out each other's risk?
It is a totally valid concern, but Webin proves that the answer is no. What's fascinating here is that even though it uses absolute values for the signal magnitude, the underlying math of HRP is inherently hedging aware.
How does that actually work mechanically?
Well, it comes down to how the cluster variance is calculated inside the branch. If a branch contains a pair of positively correlated assets, meaning they generally move in the same direction, and your signal tells the system to go long on one and short on the other, the formula mathematically recognizes that.
Because it's looking at the variance.
Because the signals have opposite signs, their product is negative. That negative product is subtracted from the total cluster variance, causing the calculated risk of that branch to drop significantly.
Oh, wow. That is brilliant.
Yeah.
So it naturally recognizes that the risk is lower because you are hedged, even while keeping the aggregate signal magnitude stable so the budget doesn't collapse.
Exactly. It's a remarkably elegant fix that requires almost zero extra computing power. It just works.
Okay, so HRP successfully sneaks our alpha into the tree, keeps the fast computing speed, and respects our hedges. But HRP is still just looking at individual assets on the diagonal of the matrix, right?
It is, yeah.
So if financial markets are entirely based on how things move together,
Mhm.
doesn't ignoring local correlations leave a massive blind spot in the tree?
It absolutely does. HRP is a huge step forward, but it doesn't look at the full local covariance matrix, how all the assets within that specific cluster move together.
Right.
To fix that, we want the tree to be smarter. We want it to use the full local covariance, and the paper attempts to build this with the second method, HRP-mu. But in doing so, Webben discovered a catastrophic mathematical bug in how these trees operate.
A bug? What kind of bug?
To use the full local covariance matrix, HRP attempts to run a local recursive mean variance optimum at each branch of the tree. But there is a massive trap here, which the paper names the sign flip pathology.
The sign clip pathology. What exactly is flipping?
It has to do with how you balance the capital budgets between the left and right branches of the tree. The natural way to do this, like the way any mathematician would write it on a whiteboard, is a sum-to-one normalization.
Okay, so just adding them up.
Right. You calculate the raw budget for the left branch and the raw budget for the right branch. Then you divide both of them by their total sum so they perfectly add up to 100% of your capital.
That makes complete logical sense. You just find the denominator and divide.
It makes sense until you introduce estimation noise. Because of the full covariance matrix, that raw sum can actually accidentally be a negative number.
Oh,
Yeah. And when you divide your capital budgets by a negative number to normalize them, you accidentally flip the mathematical sign of the entire portfolio branch.
wait, are you saying the math literally reverses your trades?
Yes. The paper notes that because of this sign flip bug, 45 to 52% of the time, the resulting portfolio points exactly backward compared to the ideal Markowitz direction.
You're kidding. So if your brilliant 6-month-in-the-making signal says to go long on tech and short on energy, this math bug forces you to go short on tech and long on energy.
That's exactly right.
And it does this half the time.
Almost exactly half the time. It completely destroys the portfolio out of sample.
That's like having a GPS that gets confused by heavy traffic and just tells you to drive backward on the highway.
Yeah.
I mean, how on earth did previous researchers or standard tracking metrics miss a bug where the portfolio points completely backward 50% of the time?
It's a great question, and it exposes a major flaw in how quants evaluate models. The culprit is the standard metric people use to track algorithm performance, which is called direction error.
Okay.
Direction error is incredibly popular because it is scale invariant. It doesn't care if you leverage the portfolio by 2x or 10x. It just checks if the geometric direction is right.
Okay, but if the direction is literally reversed?
Here is the catch. Direction error is mathematically sign invariant.
Wait, what?
To the equation, pointing exactly backward in the vector space looks identical to pointing exactly forward.
No way.
Yes. The error metric flatters the algorithm. It hides the fact that it's destroying your wealth. Webben stresses that direction error should only be used as a loose diagnostic tool, never as a final quality metric for a portfolio.
Wow. The dashboard was literally lying to the driver. So how does HRPR actually fix this sign flip pathology?
With a brilliantly simple change. Instead of sum-to-one normalization, HRPI uses L1 normalization.
Which means what in plain English?
Instead of dividing the budgets by their raw sum, it divides them by the sum of their absolute values. Since absolute values are always positive, the sum is always positive. That one single line of code guarantees you are never dividing by a negative number.
That's amazing.
It completely eliminates the pathology. The failure rate drops instantly from 52% to exactly 0%.
That is the kind of clean, satisfying fix I absolutely love. So we've successfully hacked the tree. We have HRP for transparent speed and HRP to use full local covariances without driving backward on the highway.
Right.
But honestly, trees, as beautiful and auditable as they are, feel a bit restrictive.
Yeah.
I mean, forcing messy, real-world market correlations into a rigid binary branching structure feels like trying to shove a square peg into a round hole. What if we just step away from the tree entirely?
Now you are moving into the headline contribution of this paper. The third method, CRISP,
Crisp?
which stands for Correlation Regularized Iterative Shrinkage Portfolios.
Crisp. Aside from being an excellent acronym, what makes this method so special?
So CRISP completely abandons the hierarchical tree. Instead, it solves the portfolio directly using a shrinkage operator, which is again controlled by that slider, gamma.
Okay.
At gamma 0, CRISP is a pure diagonal solve. It only looks at individual asset variances and ignores all the complex correlations. At gamma 1, it is the exact full Markowitz portfolio, factoring in every single cross-asset correlation perfectly.
And the magic happens when you set gamma somewhere in the middle,
Right.
blending the two. But, shrinkage isn't a new concept. The Ledoit-Wolff method has been doing covariance shrinkage for decades to reduce noise. How is CRISP different from the standard methods?
It differs in one vital structural way. Classical Ledoit-Wolff shrinkage methods move the entire matrix toward a central target. They shrink everything, including the individual asset variances on the diagonal of the matrix. CRISP has a unique superpower. It never shrinks the variances on the diagonal.
Why does it matter?
Because individual asset variances, like the volatility of a single stock, are univariate estimates. Statistically, they are much easier to calculate and far more reliable than the complex covariances between two different stocks.
Right, that makes sense.
CRISP assumes your individual asset variances are perfectly reliable. It only shrinks the off-diagonal entries, which are the unreliable, noisy cross-asset correlations.
Here's where it gets really interesting. Let me try an analogy here. I like to think of CRISP as a sound engineer mixing a live band.
Okay, I'm listening.
The engineer inherently trusts the individual microphones right in front of the lead singer and the snare drum. Those are the individual asset variances. They are clear, direct, and reliable. But the engineer does not trust the messy bleed of sound floating between the instruments where the guitar mic is accidentally picking up the cymbals. Those are the cross-asset correlations. Classical methods like Ledoit-Wolff just turn down the volume on the whole band. CRISP just turns down the messy bleed without ever touching the volume of the main vocals.
I love that analogy. You are perfectly preserving the reliable information and aggressively filtering the noise. And to pull this off mathematically, CRISP uses an iterative solver called scalar Gauss-Seidel.
Okay, scalar Gauss-Seidel, we need a translation for that one too. What is an iterative solver doing differently?
Instead of trying to solve the entire massive equation all at once in a single brute force calculation, an iterative solver updates the weight of one asset, then moves to the next, updates that one, and keeps cycling through the list over and over until the numbers stop changing.
Meaning it is converged on the optimal answer.
It's
So it's sort of like a mountain climber navigating down a foggy, jagged peak. Instead of trying to calculate the perfect, mathematically straight line to the bottom all at once, which might be impossible because of the terrain, they just look at the ground, find the best next step, take it, and repeat that process over and over until they safely reach base camp.
Precisely. And the key mathematical breakthrough here is that the convergence rate of this specific iterative solver is tied strictly to the condition number of the correlation matrix. It completely ignores the spread of volatility between the assets.
Meaning what for the climber?
Meaning the climber will never get permanently stuck. CRISP is unconditionally convergent. Whether you have assets with massive volatility differences or you are dealing with wild, shifting covariance regimes, CRISP won't stall out. It will always find the optimal shrunk portfolio, and it is incredibly stable.
Okay, so we have this brilliant step-by-step solver that filters noise perfectly without touching our pure signals. It must be blazingly fast, right? Like breaking computational speed records.
Well, actually, no. Not at all.
Wait, really?
Yeah.
After all that?
The paper is very transparent about this. If you put CRISP in a pure foot race against a direct Cholesky math solve.
And a direct Cholesky solve is basically trying to solve the entire Sudoku board simultaneously using brute force matrix math, right?
Exactly. If you run that foot race on an Apple M4 chip with tuned linear algebra libraries, Cholesky absolutely destroys CRISP. At 500 assets, the direct solve is up to 48 times faster than CRISP.
Wow.
We are talking 0.38 milliseconds for the direct math versus 18.2 milliseconds for CRISP.
So what does this all mean for the listener right now? If CRISP loses the 100-meter dash by a mile, Why is Wobbin presenting it as the ultimate headline method of the paper?
Because in modern quantitative finance, when you are dealing with massive real-world data sets, wall clock speed on a tiny 500-asset portfolio isn't the actual bottleneck. Working memory is the bottleneck.
Ah, memory.
Yes, the true structural advantage of CRISP isn't raw speed, it's unparalleled memory scalability.
Okay, explain how memory changes the game here.
CRISP offers what the author calls a factor model streaming variant. Because, as we discussed, CRISP evaluates the math iteratively, one asset at a time, like that mountain climber. It never actually has to materialize the dense covariance matrix in the computer's memory.
It doesn't have to hold the entire giant interconnected web of numbers in its head all at once.
Exactly. It just streams the data row by row. And the jaw-dropping statistic from the paper illustrates why this is revolutionary. Let's say you were managing a universe of 30,000 assets.
A huge portfolio.
If you want to use the fast, direct Cholesky math method, you have to generate a dense matrix with 900 million entries. That matrix takes up 7.2 gigabytes of RAM just to hold the covariances before you even start the math.
You'd need a dedicated supercomputer server farm to run that reliably.
But the CRISP factor stream, it does the exact same math, getting the exact same optimal result using only 4.8 megabytes of RAM.
Wait, 4.8 megabytes?
4.8 megabytes.
That is astonishing. This means you, sitting at home with a standard laptop, can now run institutional-grade portfolio optimizations on 30,000 assets without having to rent time on an Amazon server.
If we connect this to the bigger picture, that is exactly the point. It democratizes large-scale portfolio construction. Direct math might be faster on a tiny portfolio, but a faster wrong answer is still a wrong answer.
Right.
CRISP delivers 80 to 94% of the Oracle out-of-sample Sharpe ratio across every synthetic test panel they threw at it. It dominates the benchmarks because it shrinks the noise perfectly while maintaining a tiny memory footprint that effortlessly scales to massive investment universes.
So wrapping this all up, the heist is a complete success. We've broken into the algorithmic vault. You no longer have to throw away your hard-earned alpha signals just to get a stable, regularized, risk-parity portfolio.
Not anymore, no.
If you prefer the auditable, traceable trail of a tree method, you now have HRP for transparent speed, and HRP to leverage full local correlations without falling victim to that terrifying sign flip bug.
Right.
And if you want raw, unconstrained optimization power and memory scalability for massive data sets, you have the CRISP iterative solver. The signal-blind era of portfolio construction is officially over.
It really provides a comprehensive, mathematically sound toolkit that active managers have desperately needed for a decade.
It really does. But before we sign off today, I want to leave you with a final puzzle to mull over. Throughout this deep dive, we've seen that CRISP's ultimate superpower is that it explicitly trusts the volatility of a single asset, but it inherently distrusts the correlations between two assets.
Right, the vocals versus the bleed.
Exactly. Why is that? Why is it that the more complex the relationship gets, the more noise it naturally generates? In a world of absolute information overload, maybe the most vital skill for an investor isn't knowing how to measure every single variable, but knowing which measurements you can actually trust and which ones you need to aggressively shrink, like tuning out the bleed on a messy microphone. Until next time, keep digging deeper.